Okay, yeah, so thanks everyone. It's a pleasure for me to introduce Andreas Wallraff for today's seminar. So just to give you, I think many of you probably are familiar with his work, but just to give you a brief introduction. So Andreas did his PhD in 2000 at the University of Erlangen in Nuremberg, where he was doing kind of fundamental work on low temperature physics and vortices and superconductors. After that, he went on to a postdoc in Rob Shulkoff's group, where he did these, was working on these experiments coupling superconducting circuits to microwave resonators. These really exciting results, which kind of started this field we now call circuit quantum electrodynamics. So I think that's really exciting aspect of his work. And then in 2006, he moved to ETH Zurich, where he's been since that time, doing a lot of really pioneering work in superconducting qubits and quantum computing, and also nice work on hybrid systems. So he's been thinking about coupling superconducting circuits to other quantum systems, which is potentially interesting as we start to think about quantum networks and things like that. And today he'll tell us about really fantastic results, recent results on the surface code and quantum error correction, which I'm very excited about. So thanks, Andreas.
Good. Thank you very much, Michael and Alicia for the introduction. So yeah, it's fun to be back here. I think it's only my second larger international trip that I've done since a bit more than 2 years. And I think the last time I've been here was maybe in 2019 or so, or maybe even in 18. So thanks for having me. I will present our work on repeated error correction in a distance 3 surface code with superconducting circuits. And the experiment was done by the people listed here, and in collaboration with Alexandre Blai's group at the University of Sherbrooke, and also with Markus Müller at RWTH Aachen. And one of the main actors in this presentation here is the device, the superconducting circuit that you see in the background here. It's a device with 9 data qubits and 7 auxiliary qubits. And I'll explain it to you in more detail later, but the qubits are the yellow structures. And the yellow structures, the qubits, are coupled in many different ways to microwave frequency resonators and make use of this concept of circuit QED, where microwave photons couple coherently to superconducting qubits, both to mediate interactions between neighboring qubits, also to read out qubits with high efficiency, which is particularly important in quantum error correction settings. So, and I think this is kind of a nice device that we did this quantum error correction experiment on. And maybe one of the aspects that is also special is that you get to look at a device this size, with 17 qubits. I think there's probably other devices this size around, but typically you don't get a chance to look at those anymore.
What is the length scale on this thing?
That's the chip is, so you see it's up there, and the chip across this, you see the full width, and it's about 14 by 14 millimeters roughly. So it's not very small. And you even I'll show a picture where you see some of the items you can see with the bare eye when you hold the chip into the light. All right, so this is one of the main actors, obviously, but then there's a team at ETH who did this really very nice experiment. And here you see a picture of the experimental part of the team, and the theorists were not on those, but I think those ones more as well. And I should also point out that this device was put into a cryostat just at the beginning of COVID, and it took about a year and a half or so to get these experiments done. And we started on a logical qubits program that is funded by IARPA actually 6 years ago. So it took a while to get going on this. And we were happy to see that we actually crossed the finish line at sometime at the end of last year. So as Michael also said, so there was a picture of the current team working on this experiment on the past slide, and we've now been at ETH for 16 years, and we've worked with quite a number of students and postdocs. And some of the postdocs now have their own labs, which is very encouraging to see. And quite a few of the other students now work in industry around quantum, either at startups or companies that provide tools in and around quantum information processing. So I think this is really developing very positively. And ETH has also a new quantum engineering master's program, which students find very attractive. So we get about 50 students coming into that every year, and many of those show up in our lab and wanting to work with us for their projects. Okay, maybe for I guess you're all experts in quantum information processing, and so you've probably heard in one way or the other about this previously, but to get started in this presentation, I just remind you that there was this really nice experiment on a quantum computational advantage that Google has done, and it's maybe 3 years ago now, but I still think that it kind of represents the state of the art in terms of the size of devices and complexity of experiments that can be done with superconducting circuits. So I think it's still the, or maybe one of the most complex experiments with superconducting circuits that has been done. It involved 53 qubits. It had state-of-the-art gate fidelities or so, which are still challenging to achieve even these days across large devices. And it's been a milestone in the sense that it demonstrated advantage over conventional computers in one task. And usually I would point out that this task was maybe not particularly useful, but it proved a point that that you can calculate something on a small quantum computer that would be hard to simulate on a classical computer. And well, okay, so you could ask yourself, this was clearly a milestone, but did it solve all the problems that one needs to solve for practical quantum information processing? Yeah, probably not. I think it also didn't create the type of breakthrough where everything was then easy from that point forward, or it showed nicely that you can get to a certain stage and demonstrate that you can calculate a quantity that would be hard to simulate on a classical computer, but we need to go further than that. And I think economically viable, noisy intermediate scale quantum information processing needs significantly larger number of qubits. And in particular, what we all have in mind is at some stage to use quantum computers in a universal way. And for that to happen, they need to be fault tolerant. And this quantum computational advantage experiment clearly was not very fault tolerant. And I'll dwell a little bit more on that in a second. So I think there's still lots of work to do, yeah, and while maybe if you look at the media or so and ask yourself how close are we to a truly useful quantum computer, and it seems very near, but I do think that there's lots of interesting work that remains to be done, both on a technological level but also on a conceptual level. So let's maybe look a little bit more at this experiment from Google. So there were 53 qubits on a 54 qubit chip. It had very good 2-qubit gates with gate errors that were less than 1%, both for single qubit gates and for 2-qubit gates. The readout was pretty decent. It was less than 4% error per readout. And they ran a fairly long gate sequence on this device, which involved all of the 53 qubits and ran to a depth of essentially 20 consecutive 2-qubit gates, which got enacted over all this device. Here in the device, you see every cross here shows a qubit, and every box is a coupler between qubits. So the experiment was essentially designed to do something that would exaggerate the difference between a classical computer and a quantum computer. It essentially ran an algorithm that would execute a random gate set across these 53 qubits with a depth of about 20 consecutive gates, and it would make a very complicated but essentially structureless entangled state between all of the 53 qubits. Yeah? And that entangled state is very difficult to recreate on a classical computer just because of the size of the Hilbert space that you would need to have under control. And if you create this essentially random complex and entangled state, or so that is also the aspect that makes it very hard to simulate on a classical computer. If you were simulating a quantum problem that you were actually interested in, usually the quantum problem would have some sort of structure to it that makes the problem interesting. And that structure to the problem also makes it then shrinks the gap between sort of the quantum advantage that you would get and the difficulty for the problem to solve on a classical computer. So in some sense, this was cleverly chosen to make this point of quantum advantage, but the difference shrinks as soon as you look at a real problem that you're interested in. And so maybe the other aspect that was still important to figure out, so you run essentially 1,000 gates in sequence on this 53 qubit device, and the state that you've created in the end, if you compare that state to the state that you actually intended to create if everything was perfect, if there were no errors, the fidelity as characterized by this cross entropy fidelity was only 10 to the minus 3. Yeah? So the state is not very similar to the one that you would have ideally created. Nevertheless, despite that, it would still be very difficult to create that state on in a simulation on a classical computer. So, and this was essentially then limited by the coherence of the qubits and the limited gate fidelity. And what this also clearly shows is that if you want to use that for some real problem, say you want to calculate the ground state energy of a larger molecule, or you need to deal with these errors and preferably use an error-corrected fault-tolerant quantum computer. So for that reason, in quantum information processing in general, but also with superconducting circuits, clearly there's maybe two goals currently that are followed. So first is to extend this realm of a noisy intermediate scale quantum information processing to systems with larger numbers of qubits, trying to identify interesting settings where you can learn something from doing these types of simulations is one direction that many labs and companies follow. And the other one is to try to realize fault-tolerant quantum information processors. And this is what this talk today is going to be about. Good. So, all right, just to remind ourselves for why we actually need error correction in a quantum computer. Or so, the first thing to notice is that even though if you maybe work with ions, you feel that the energy relaxation rate of ions is very, very slow. But any quantum system in the end decays from its excited state to the ground state. So here you see a Bloch sphere that represents the eigenstates of a qubit. And if you prepare a superconducting qubit in the excited state, it will decay after some time scale to the ground state. And if you use these states for storing quantum information in your systems, this will constitute an error. And principle matters, any quantum system, due to its coupling to the vacuum fluctuations of the electromagnetic field, will decay from its excited state to the ground state on some time scale. And so this process is spontaneous emission then, and you can't get rid of it, even though that you could maybe choose systems where the spontaneous emission rate is small. But there's also other ways how these bit flip errors could occur. For example, maybe your system isn't fully in the ground state because there's some background temperature that every now and then excites a qubit from the 0 state into the 1 state. Or your control of the qubit state could be faulty. So you don't prepare the wanted states with an arbitrarily high accuracy. And so these limitations lead to errors, and if you want to realize a fault-tolerant quantum computer, you need to correct these errors. And one of the ways how to characterize how often, for example, this energy relaxation errors occur for a single physical qubit is by measuring the expectation value of the Pauli Z operator, which is something that we'll look at for error-corrected qubits later, and therefore I show it here also. So when you measure the excited state population in a typical one of the physical qubits on the device that I showed on the title slide, you and you average over repeated measurements, you typically see a decay of the qubit excited state to the ground state on a time scale for superconducting qubits, which is maybe several tens to several hundreds of microseconds. So this is one type of errors that occurs in a quantum computer. But clearly, there's also another type of error, since the quantum computer also works with superposition states, and also superposition states can undergo errors. And one of the ways how this is represented on this slide here is that, trying to handle the somewhat unfamiliar remote here, is that if you think about superposition states like the 0+1 superposition state, if there's an error in the phase occurring, this 0+1 superposition state could turn into a 0-1 superposition state, and that would constitute a phase flip. And in a quantum computer, you would need to deal both with bit flips and also with phase flips. And so where could these phase flips come from? So these phase flips would come from environmental fluctuations of the field, for example, the field that defines the energy level separation of your qubit. It could again come, these phase flip errors could come from inaccuracy in your control, and obviously also energy relaxation itself destroys the phase of your physical qubit. And
Andreas,
one of the
may I
ways
ask
how
a
to look at, sure. There's a question from the online audience. Just go ahead.
Yeah, thanks. It's Nicole Younger-Halpern.
Yep.
So you've described bit flips and phase flips. I kind of got the impression that you were describing the errors that are particularly relevant to superconducting qubits. These are the types of errors that we study in theory and quantum computation courses. Are they also the worst offenders in a superconducting qubit platform, or do you tend to see a lot of, say, correlated errors?
Yeah, that's a very interesting question. So, for example, in our experiments, we don't see a lot of correlated errors currently. Sort of the correlations are not strong. So our experiments didn't show indications of what, for example, Google has observed, that every now and then they have maybe a fatal event where a cosmic ray or so hits their device and creates lots of errors in qubits in the vicinity of that. So when we analyze our data, we don't see lots of these correlated errors. And the way how we do this particular experiment, with using spin echo, for example, it also looks like we're suffering in a relatively balanced way between phase flips and spin flip, phase flip and bit flip errors in our device. Yeah. Obviously, understanding the physical origins of the errors is very important to improve the performance of every individual component. But indeed, I think our data didn't show lots of correlated errors. But when you start looking more carefully, I think maybe one has to revisit that question.
Okay, thank you.
All right, thanks for the question. Okay, so there's this, and maybe one of the reasons why I introduced this bit flips and the phase flips is because in comparison to sort of classical error correction codes, where you essentially only deal with bit flips, the quantum computer now has to deal with two different types of errors simultaneously in error correction schemes. And if you looked at the historical development of error correction in quantum computers, it also started out typically first with trying to correct one type of error. And one of the experiments, or the experiment that I'll be presenting to you today, is the first one that actually manages to both detect phase and bit flips and also correct for them. Okay, so how do you deal with these errors then in quantum error correction when you use encodings that make use of qubits? You're trying to deal with bit flip errors and phase flip errors. And essentially, the challenge that you're trying to address is that you need to find a scheme, identify a scheme where you can detect and correct for errors, while the measurements that you need to do to even notice whether errors occurred don't collapse the quantum state that you're trying to encode. Because, for example, if you think about trying to figure out whether a phase flip occurred on a single physical qubit in a superposition state, you would perform a a measurement on that superposition state, and that would collapse the qubit either in the ground or in the excited state upon that measurement. And that you would certainly want to avoid in a scheme where you're trying to detect for errors occurring in the encoded quantum state. So for that purpose, you actually decide to encode quantum information in the state of a logical qubit, and that actually proceeds by distributing the quantum information over many physical qubits. And here you see a picture of what that could work, how that could look like. So this is every dot here in this diagram represents a qubit. There's 5 by 5 physical qubits shown in red, and so 25 in total, and 24 qubits which are colored in green and in blue, which are auxiliary qubits, which are those which you use to actually detect whether errors have occurred or not. And then the goal in this error correction scheme here is to actually encode quantum information in the state of many physical qubits. And instead of measuring all qubits directly, you measure a symmetry property of the field of the qubits that you store the information in. And using that symmetry property, you can actually reveal the presence of errors, but not destroy the encoded quantum state. And how that works, I'll give some examples for in a second. Good. So so this for the general motivation for this talk. I'll spend 3 slides to tell you a little bit about superconducting qubits. I think many of you have heard many talks about superconducting qubits and probably know the basics, but since maybe this is for a general audience, I'll say a few words about it, and I'll talk about my quantum error correction experiment that we did in our lab, and at the end, if there's time, we can talk a little bit about future challenges. Okay, so this is maybe too basic for this audience, yeah, but I think one of the aspects that I like in understanding how electronic circuits work quantum mechanically is to just notice that the degrees of freedom in an electronic circuit can be either expressed in terms of charge, for example, a charge living on either the lower or the upper plate of such a capacitor, and you could make superposition states and represent them pictorially this way. And the charge degree of freedom is one of the conjugate variables that you can use when you write down the Hamiltonian for any electrical circuit. Or you could think about currents flowing through loops, either clockwise or counterclockwise, or in a superposition of clockwise and counterclockwise. And noticing that charge and flux are conjugate variables for electronic circuits is sort of very useful, because that's something that you do in your first quantum mechanics class. Essentially, when you learn about the quantum mechanics of a hydrogen atom or matter waves, you look at physical systems and write down their total energy, their Hamiltonian function in terms of the conjugate variables, namely the position and the momentum. And then you replace position and momentum conjugate variables with their operators, and then you have a Hamiltonian operator with which you can then solve Schrödinger's equation. Yeah? And the same thing you can do with superconducting circuits, expressing the total energy in terms of charge and flux conjugate variables, replacing them with their corresponding operators, and then solving the Schrödinger equation. And that you can do for any electrical circuit that you could draw, and figure out what the energy level spectrum of that circuit is, for example. Okay, and so what we do in our lab is we essentially, as Michael also said in the introduction, we use very frequently 2 types of circuits. So one circuit is a harmonic oscillator type circuit, where we combine an inductor with a capacitor effectively, that then has a quadratic Hamiltonian both in the flux phi and the charge q, and behaves like a harmonic oscillator, the resonance frequency of which is set by the size of the inductor and the size of the capacitor. And this then has excitations, has this linear excitation spectrum of the harmonic oscillator, and these excitations we sometimes or we frequently lovingly call photons. Yeah, even though that if you're maybe more into optics, you may question why we call these excitations photons in our setting here. And as long as you use inductors and capacitors which are linear, you will end up essentially with a linear excitation spectrum. Any circuit that you would build would be a combination of harmonic oscillators. And what makes life then quite a bit more interesting is to replace this linear inductor here with an anharmonic inductor, and this anharmonic inductor in superconducting circuit is the Josephson tunnel junction. And this anharmonic inductor, which is lossless, creates a non-equidistant energy level spectrum for this anharmonic oscillator here. And one of the interesting ways how to, or like very simple ways how to see why that makes sense is, for example, if you look at this LC resonator here, and you consider the flux and the charge as the two conjugate variables, you can write down the potential energy in terms of the flux, and that's quadratic in the flux variable, yeah, because the magnetic energy is quadratic in flux here. And then the energy level spectrum is just the eigenstates of an effective particle with a mass that scales with 1 over the capacitance of this circuit, that then has equidistant energy levels. And if you replace that inductor with a Josephson junction here, the magnetic energy is now not quadratic in the magnetic flux, but it's cosinusoidal in the magnetic flux. And therefore, this cosinusoidal potential, as you go up in energy, sort of opens up. So the oscillator essentially softens, and that brings the energy levels closer to each other. And that then creates non-equidistant energy levels in this potential well here. And the fact that they are now non-equidistant allows you to excite certain transitions by irradiating this superconducting qubit with a microwave frequency source that is tuned in resonance with a specific transition. Okay, so that's all I wanted to say about superconducting qubits at that level. And essentially in this picture that I showed you on the title slide, we bring these two combined circuit elements, harmonic oscillators and qubits together to build up more complicated devices. Good, so let's look back at this, at the way how we realize fault-tolerant quantum information processing in quantum error correction in a particular approach that is known as the surface code. And so here we encode quantum information in multiple physical data qubits, which are shown in red. And we use this interspersed auxiliary qubits in green and blue to measure the symmetry properties of the quantum states of the data qubits into which we encode the logical qubit state. And from information that we can extract from looking at the values that we get out of these so-called stabilizer or parity measurements, which I'll explain to you in a second, help us then to detect errors and then also correct for them. So what is special about the surface code? One aspect that is special about the surface code is that it's realized with qubits in a planar lattice. So you can arrange all the qubits in a planar lattice and lay them out on your device in the way that I showed to you on the title slide. It's a topological code, and that means in this context also that you can actually correct and or you detect and correct for errors by local operations on this lattice. And so why is the surface code so interesting? The surface code is interesting because it's the quantum error correction code, which is known to have the largest threshold that we know about so far for making the code operate successfully, suppressing physical errors occurring on the logical qubit. And the threshold is around 1% for that. And many of the other codes that we know about have much more stringent thresholds than that, and therefore it's interesting to look at this so-called surface code, which encodes quantum information in physical qubits. And there's also other approaches that use harmonic oscillator states, for example, for error correction, like in bosonic codes, for example. But my talk today will be exclusively about this qubit-based quantum error correction approach. Good. So how does this work? So here you see again this grid of data qubits with the X and Z type auxiliary qubits, and these X and Z type auxiliary qubits are used to measure symmetry property of the neighboring qubits that sit in a plaquette. You see, for example, if you look at this plaquette here, there's 4 data qubits that couple to this Z-type auxiliary qubit. And the Z-type auxiliary qubit you can now use to measure the parity of the neighboring data qubits. And in the end, in this logical qubit, you are trying to encode quantum information in states that have an even parity. That means that where the number of excitations in the data qubits is even, so where you have 2 1s or 4 1s, then one way how you can actually detect that an error has occurred is one of the qubits in the excited state goes from the 1 state to the 0 state, and that will change the parity of that state from even to odd, because you go from a state that had an even number of 1s to a state that had an odd number of 1s. And so how do you do that? How do you realize that in the surface code? So technically, or maybe theoretically speaking, you would say that you measure the product of this 4 Pauli Z operators of the 4 neighboring data qubits in this plaquette. And you could do so by either trying to measure these Pauli Z operators directly, or using or this product operator directly, or using this so-called auxiliary qubit-based approach, which can figure out the parity of 4 data qubits that sit in this plaquette. So how is that done? So this is done by executing a set of controlled NOT gates between each one of the data qubits and one auxiliary qubit here shown in green. And so these 4 logical 2 qubit gates, the 4 C0 gates, essentially measure the parity or project the parity of the 4 data qubits on this auxiliary qubit. And I'll give an example for how that works more explicitly in a second. So, and in the surface code, you need to do this operation in 2 bases. One's in the Z basis to look at bit flip errors occurring, and one's in the X basis to look at phase flip errors occurring. And you can do this stabilizer or parity measurement in the X basis essentially by executing the same set of 2 qubit gates, but flipping all the data qubits from the Z into the X basis by applying pi half pulses to every single one of the data qubits first. Okay, and then in a surface code, you essentially execute these types of stabilizer measurements in every round of the surface code on every plaquette that you see in this so-called distance 5 surface code with 25 data qubits. And while you do that, you can detect whether the parity of any of the data qubit states has changed. And if the parity has changed, that actually identifies that an error has occurred. And then from the pattern of changed parities, you can figure out which one of the data or auxiliary qubits has actually undergone an error. And for that to work well, you do all these gates. So there's quite a bunch of single qubit gates and also a larger number of 2 qubit gates. And obviously, for that to not introduce additional errors into your circuit, you need these gates to be of high fidelity. And what is also particularly important, and where maybe our lab has made major contributions, is that at the end of every one of these stabilizer measurements, you need to read out the auxiliary qubit chain state to determine what the parity actually was. So while you execute the surface code, you need to be able, during the execution of the code, to repeatedly measure the auxiliary qubit states without disturbing the data qubits. And so these mid-cycle repeated measurements are something that is very challenging in many qubit architectures, and for example, also particularly challenging to realize in ions and ion-trapped quantum information processors, but also difficult in superconducting circuits. Okay, as I said, so maybe in a bit more detail, or as an example, how does this parity measurement work, or the stabilizer measurement work for the example of just a 2 qubit Z parity. So here you see 2 data qubits in the state 0 and an ancilla qubit or auxiliary qubit in the state 0 as well. And so these C0s here, if you run them between the data qubits and the ancilla qubit and the control qubits are in state 0, they will not change the state of the ancilla qubit or auxiliary qubit. If the data qubit is in state 1, the first C0 gate will flip the ancilla from 0 to 1, but the second C0 gate will flip the ancilla qubit from 1 to 0. And so the auxiliary qubit ends up in the state 0 after C0s were executed with 2 data qubits in state 1. And so this gate sequence then allows you to determine the parity of the data qubits. So both the 0, 0 and 1, 1 state are even parity states, and this is indicated by the ancilla qubit essentially staying in the ground state. So if you now look at the other situation where one of the data qubits is in 0 and the other one is in 1, then you clearly see that only one of the C0 gates will flip the ancilla, and the ancilla will go from 0 to 1, and in that way indicate that there was actually an error occurred, and that the parity of the data qubits has changed from even to odd in this case. And if you do this in a quantum computer, yeah, you would decide in an error correction setting, you would decide to encode all your quantum information in even parity states. Yeah, and if one of the data qubits swaps its state from 1 to 0, yeah, then the parity would change, and these stabilizer measurements would detect that. And you can see the presence of such an error by just looking at your auxiliary qubit and seeing that it has flipped from 0 to 1. And this you essentially do not only for so-called weight 2 stabilizers with 2 data qubits, but for every one of these plaquettes with 4 data qubits on a plaquette. Good. So on this slide, I have an example a bit on how this works with a so-called distance 2 surface code. A distance 2 surface code has 4 data qubits, 2 by 2 data qubits that sit in the square plaquette that you see here. And these 2 by 2 data qubits have then, you measure 3 stabilizers, 2 weight 2 stabilizers here at the edges in green in the Z basis, and 1 weight 4 stabilizer in the X basis in the center. Okay, what are these stabilizers? Here the qubits are labeled D1, D2, D4, and D5. And the reason for this maybe slightly odd numbering is because they are part of this larger distance 3 surface code that we'll be discussing in a second. So the weight 4 stabilizer is this product of these 4 X operators, and the weight 2 stabilizers are the products of the 2 weight 2 stabilizers that you see here. And the stabilizers commute with each other, and because they commute with each other, they have common eigenstates. And so here's an example for such a common eigenstate that you could use to define the logical 0. So the logical 0 here is now a superposition of all data qubits in the ground state, all in 0, or all data qubits in the excited state, all in 1. And clearly, this is an even parity state, or it has 4 1s and 4 zeros. And so now you could turn this logical 0 state in even parity into a logical 1 state by operating on it with a logical operator. And the logical operator is just the product of 2 X operators. In this case, the 2 X operators are shown here. It's either the product of X on 1 or X on 4, or you could also use X on 2 and X on 5. And so if you flip the first and the third qubit in this list, yeah, then you make the logical 1 state. And you see that the logical 1 state also has an even parity. So it has an equal number, has an even number of 1s in every one of its components. And then the logical superposition states, the plus state, which is the superposition of logical 0 and logical 1, is written down here. And you can turn the logical plus state into a logical minus state by acting on it with a product of 2 Z operators, which are shown here, for example, by the Z operator on the first qubit and the Z operator on the second qubit. Will then flip the signs in the second component of the state and will turn the logical plus into a logical minus. And so this gives you an example for how in the surface code the logical states are structured. Yeah, and you can just look at them and see that they are all of even parity. And the same concept you then use for an arbitrary size surface code, and then it gets more complicated to look at. And if you like to look at it, if you, for example, look at it from a theorist perspective, maybe it's good enough for you to look at the physical, at the properties of the stabilizer operators and see that they commute and that you can construct a set of eigenstates that fulfills these requirements. So the logical operators anti-commute with each other and they commute with the stabilizers. And so on this we have done an experiment about 2 years ago with 7 superconducting qubits and realized this distance 2 surface code. And the distance 2 surface code, you can run an error detection experiment, but not an error correction experiment. So you can use this scheme that I've mentioned. You can measure stabilizers and look whether your auxiliary qubit states change, where the change of auxiliary qubit state indicates a change of the data qubits from even to odd parity. But there's not enough information to understand where did the error actually occur. Yeah? So you need more qubits to actually figure out on which of the data auxiliary qubits the error did occur. And the first size surface code that achieves that task is this distance 3 surface code. And it has 9 data qubits that you see here are shown in red. And then 8 stabilizers get measured. And there's 4 weight 2 stabilizers and 4 weight 4 stabilizers. And half of them are measured in the X basis and the other half are measured in the Z basis. And the logical operators, which you act on your logical qubit to turn a logical 0 into a logical 1 or a logical plus into a logical minus or so, are listed here. And they're always kind of the products of the Pauli operators along such a line that is indicated here for the Z basis or for the X basis vertically and for the Z basis horizontally. And then you can construct eigenstates again, yeah, and now this gets more complicated to look at, yeah, and that's maybe shows you that why you wanted to look at maybe a distance 2 surface code initially to see how the states are constructed. But this is now a distance 3 logical ground state that you see has the properties that I mentioned to you previously. Okay, and that's the distance 3 surface code which we had realized in our experiment. Good, so here's the device that I showed to you in my title slide. This 14 by 14 millimeter device with 17 qubits shown in yellow. Then every qubit can be controlled with a microwave frequency drive line that is shown in pink here, so that you can use to do single qubit gates. Then there's these green lines that tune the qubit transition frequency, and that access to the qubit transition frequency we actually use to initiate 2 qubit gates, the C0 gates that I've mentioned to you. And the qubits couple to each other for the purpose of creating these C0 gates through these blue microwave transmission lines that essentially mediate a capacitive coupling between neighboring qubits along this square lattice that I've shown to you. And then maybe a key feature, the technical realization of which I'll not dwell much in this talk, is this combination of microwave resonators shown in red and blue here, which are used for reading out the qubit state. And these microwave frequency resonators get actually shifted in frequency, conditioned on whether the qubit is in the ground or in the excited state. And that frequency shift you can use to perform a high fidelity single qubit readout, which is essential to understand what the auxiliary qubit state is at the end of the stabilizer measurement. Good, and here you see I put on top of this device here, I put the plaquettes in green and blue, which indicate the location of the stabilizers. And in the middle of these plaquettes, you see the auxiliary qubits, and at the vertices of the plaquettes are the data qubits. Yes, there's a question.
Measurements that we're using ancillas to measure the stabilizers. So why do you need to have the readout line for all the qubits if you only want to measure ancillas?
Okay, so the question is, why do we need readout lines for all the qubits while we need to only measure ancillas? In the end, we need to characterize whether the surface code actually worked, and we need to be able to read out the data qubits at the end of the process. And so all qubits need to read out, while during the surface code cycle, only the ancilla qubits or the auxiliary qubits get read out. But at the end, the data qubits get read out to determine the final state of the logical qubit and to act with the correction onto that logical qubit state. Good. So maybe just a few words about the device performance. Maybe I'll just be brief here. So the device is pretty good. So the coherence properties are several tens of microseconds. The single qubit gates have an error that is maybe 0.1% in 40 nanoseconds. The 2 qubit gates have errors of about 1.5% or so. Yeah, that's pretty good. There's maybe architectures where this is a little bit better, but in a device this size is pretty good. And maybe what is particularly important in our setting is that we're actually able, for all of the 17 qubits on this device, read out all of the qubits with a state assignment fidelity that is about 1% if we want to only distinguish the ground and the first excited state from each other. But what is maybe even more important is that we can do a 3-state readout with about 2% readout error, and that 3-state readout allows us to measure leakage out of the computational states of our qubit. And leakage is one of the most detrimental aspects in quantum error correction that will destroy the functionality of your error correction code. And so we can detect these leakage states explicitly with high fidelity and in short time. And our readout time is about 300 nanoseconds to 400 nanoseconds, depending on the qubit. And the cumulated readout time is about as long as the time that it takes us to measure a set of stabilizers in this device. So it's very well balanced between gate performance and gate execution time and readout time. And if this was very unbalanced or so, for example, if you have a slow readout, you lose out in your error correction cycle by a fair bit. So I've shown to you the device. Here's a picture of the device mounted in a PC board for the experimentalists. So there's 48 microwave connectors to control this. So this has to be packaged nicely to get the performance out of the device that you need. And that device then goes into a big dilution refrigerator with lots of signal conditioning components. And this starts to get sort of complicated to just get all the control electronics working well on even on this size scale for a distance 3 surface code with 17 qubits. So here's all the electronics that you in a cleaned up version of a setup that we've just recently put into action for these types of experiments. All right. So obviously no work ever stands on its own. Yeah, as I mentioned also in the introduction, there's been quite a bit of work on quantum error correction previously, also in many different physical systems and NMR and ions, and particularly here at Maryland, there's really nice work with ions on error correction as well. And initially there were experiments where there were only bit or phase flip errors that got corrected. Then there were experiments in which both bit and phase flip errors have been corrected, but only in a single cycle. And in a quantum error corrected system, you want to do that across many cycles. Then there were repeated quantum error detection experiments in distance 2 surface codes, where both X and Z errors were corrected across many cycles, but in a code that was too short to also identify where the errors occurred and therefore correct for them successfully. And then at the end of last year, we then managed to get our distance 3 surface code to actually correct for errors as well. And there's an interesting color code experiment by Honeywell done that is also repeated. And then at the end of last year and at the beginning of this year, both Jean-Roy Pan's group and IBM also had a distance 3 quantum error correction experiment put out on the archive. All right, so now all the bits and pieces are together and we can see how well this performed. So we can look at these stabilizer measurements in a little bit more detail. So I've explained to you the stabilizer measurements in terms of C0 gates acting between data qubits and auxiliary qubits. In our devices, actually what we implement are not C0 gates, but so-called controlled phase gates that are displayed as shown here. And so we run C phase gates between every data qubit and the auxiliary qubit, 4 of them in sequence. We essentially perform a Ramsey experiment by putting the auxiliary qubit first in a superposition state. And then these controlled phase qubits, rather than flipping the target qubit, when the data qubit is in the state 1, these C phase gates change the phase of the target qubit when the data qubit is in 1. So when there is an even number of data qubits in the state 1, it will flip the phase an even number of times of this auxiliary qubit, and then effectively leave the qubit in the original state. While when there's an odd number of data qubits in the 1, it will change the phase of the auxiliary qubit and then flip this auxiliary qubit state, which you can read out. And if essentially this implements the same functionality as the CNOT gate that I've explained to you previously. And as I mentioned and explained already before, you can do this measurement in a Z basis, and you can swap the basis of the measurement by just turning all the data qubits from the Z into the X basis by applying pi-half pulses to them. And what is maybe also interesting in our experiment is that we do a spin echo pulse in the middle of our gate sequence that deals with residual couplings between our qubits. Good, and then you can look at how well that works. Is this circuit able to measure the parity of the data qubits? And for doing so, for each plaquette, you prepare all the data qubits in all possible basis states. And here you see all possible basis states listed from all zeros to all ones. And you then see all the basis states that have an even number of ones create a positive parity signal or positive stabilizer value, while all the data qubit states where the number of ones is odd create a negative stabilizer value. And you see that our stabilizer circuit is able to distinguish the parities of these data qubits. And the average error for that experimentally is about 6% here. And it's a bit worse than what we would predict from doing numerical simulations on the performance of these circuits. But overall, I think we would say that we understand the origin of these errors fairly well in our devices. And so on this device, we don't only have one stabilizer, but 8. So here's the characterization for all of the 8 stabilizers, and they all work. The weight 2 stabilizers have an average error of about 4%, while the weight 4 stabilizers have an average error of about 8%. And that's also not so surprising, because the error essentially comes from the cumulated error of the 2 qubit gates. So if you have a bigger stabilizer with more 2 qubit gates, it accumulates more error, and a stabilizer error is larger. And it's about a factor of 2 larger than for the weight 4 than for the weight 2 stabilizers. And we again find a reasonable qualitative agreement with our master equation simulations. So and then you put this essentially all together and see whether it works. So here you now have this starting to be a bit more involved quantum circuit diagram for in blue and in green the 8 stabilizers and the 9 data qubits. And in a first step, we essentially run all the Z-type stabilizers simultaneously in a sequence. And then in a second step, we run all X-type stabilizers in a sequence. And if you count gates, you see that you get 24 2-qubit gates per cycle, and the according number of single qubit gates, both for the spin echoes and for the basis changes. And what is important for the performance of the surface code experiment is that we're able to, while we execute the coherent gates that implement one type of stabilizer, we can actually read out the auxiliary qubits of the other type of stabilizer simultaneously. And that is critical to make sure that the gate sequence remains short. And so here, this gate sequence for the stabilizer distance 3 measurements has only a duration of about 1 microsecond. And I think the IBM experiments currently take 5 microseconds. And I think the Honeywell ion experiments, where you need to shuttle ions around, they take 5 orders of magnitude longer than these superconducting circuit experiments. Good, and then we can see, does this work? Yeah, and we essentially initialize the logical 0, the logical 1, and the logical plus and minus superposition states in this circuit, and then measure the expectation values of the logical operators at the end. Okay, and so one thing that is important, but that I will not dwell on here further, is that, as I mentioned, leakage is an important problem in these devices. And since we are able to do 3-state readout, we actually do detect leakage of both the data and the auxiliary qubits in our experiments, and we reject leakage in every round. And the performance criteria that I mentioned to you, they are leakage rejected, and the leakage per qubit per cycle is relatively small. Good.
That could be corrected in the future.
So the question is, can leakage be corrected for? So first, there's various things that we did to suppress leakage, to design the device in a way that leakage is small. There's also active ways to detect leakage and then correct for it, but this will make the circuits more complex, and we haven't implemented that yet, but there's ideas how to deal with that. Okay, so one of the interesting aspects is how to actually decode the error syndromes, like what errors have happened and where. And I think I don't have time to go into the details. But here you see, for example, the lattice, our surface code distance 3 lattice, and assume you had an error on the data qubit, on this particular data qubit. And this would then lead to 2 auxiliary qubits indicating that there is a Z error that had happened. And from this so-called syndrome, yeah, auxiliary qubits indicating an error, you can decode what type of error and where it had happened. And you do so by constructing a so-called syndrome graph. And so the syndrome graph essentially looks for a number of consecutive time steps that your surface code cycle works, for which auxiliary qubits indicated an error. And from this pattern of indicated errors, you can figure out where the error occurred and then correct for it. And this gets done with a so-called minimum weight perfect matching algorithm. And we've trained that minimum weight perfect matching algorithm from data that we've measured on the device itself. So we're training data for this decoder that came from the device itself. And so therefore, it's essentially a model-free approach. Okay, and so then we ran this and looked at how well this worked. And this will then wrap up my presentation. So we prepared the logical 0 state, the logical 1 state. For doing that, you essentially prepare all the data qubits in a separable state that is written down here. You prepare all the data qubits in a different separable state for the logical plus and the logical minus state. And then you perform n cycles of quantum error correction. You read out all data qubits at the end, and that answers also the question that was asked before. So why do you need the readout for these other data qubits to be able to look at your logical qubit expectation value, to verify what state you have and to be able to correct the final state based on your measured syndromes. And what we then plot are essentially the expectation values of the logical Z operator and the logical X operator. And you can do that by essentially reading out the qubits, the data qubits that belong to that operator. And then you average over it, and you average over it while correcting for the errors that occur in every single cycle. Okay, and so here's then essentially the final plot. So here's plots that show the logical expectation value versus number of quantum error correction cycles, both in the X basis and in the Z basis. So for the logical 0 and logical 1 in this top graph, the logical plus and the logical minus in the bottom graph. And so this has implemented error correction using this minimum weight perfect matching decoder. And we find that the logical lifetime is around 17 microseconds, which is much, much larger than the 1 microsecond cycle time about. And similarly, we find that the logical coherence time, so the T2 logical, is about 18 microseconds, again, quite a bit larger than the logical cycle time. We also compared these results to how well we would expect our surface code to perform based on the coherence properties and gate fidelities that we've measured, and we find reasonably good agreements. And based on the assumptions that we make, the simulation using some form of master equation simulation provide a bit better logical coherence times than what we measure, and I could explain why that is at the end. And so what we then do is you could ask yourself, okay, how good is this now really? So one aspect that you notice is these logical coherence times, they are about a factor of 2 worse than our physical qubit coherence times for this particular experiment. So to further analyze how good this experiment performs is we've calculated the logical error probability from this decay curves of the logical expectation values. And then we were interested in the logical error per cycle that occurs in this experiment. And this logical error per cycle is about 3%. So that gives you 3% as the probability in a given cycle for an error occurring on the logical qubit. And I think this is kind of an interesting number to characterize how well the system works, because you achieve a logical error rate of 3%, even though that you concatenate 24 2-qubit gates, which each have an error of 1.5%. And the reason why this works is because your decoder can actually detect these errors and then correct for them. So is 3% now small or large? And one aspect that we looked into is how this logical error per cycle rate compares to the physical 2-qubit error, which is 1.5%. And the reason why we make this comparison is because, for example, if you would now think of doing logical gates between 2 logical qubits, you would ask yourself, okay, how well would you implement the logical 2-qubit gate? And if you are in an architecture where you, for example, are allowed to perform a transverse logical 2-qubit gate, then the relevant scaling parameter is actually the physical 2-qubit gate error of 1.5% or so. And so we see that the two numbers are not so far from each other, and we've then done a simulation where we ask ourselves, okay, when does this cross over? Like, how much do we have to improve the physical properties of our gates and the coherences of our physical qubits to pass this crossover for this logical 2-qubit gate operation? And we've done that by improving the physical properties of our device by a factor of 2, 5, and 10 in our numerical simulations. And we think that roughly improving everything about our device by a factor of 2 would allow us to get the logical error per cycle sort of to a level that it would then be smaller than the logical error than the physical error per 2-qubit gate. And this would then allow us to then implement meaningful 2-qubit gates in this logical qubit setting. So we think that the break even is sort of within reach. This experiment hasn't reached the break even yet. There was also another aspect that one could look at. For example, if you do a Pauli error model, you can try to simulate how good the properties of the device would need to be to reach the physical break even. And there's this work by Austin Fowler, and we've also done some numerical simulations, which we're still in the progress of wrapping up. And we think that we're maybe somewhere around a factor of 2 off this break-even point with the device properties that we've demonstrated. Good, so that wraps up my presentation. So we've implemented a repeated quantum error correction in the distance 3 surface code. We have a low logical error per cycle. In the next round of experiments, we would like to actually implement feedback on our auxiliary qubit states and reset our auxiliary qubits. We would like to increase the code distance, which is challenging. You have to go from distance 3 to distance 5, means essentially you now need 49 qubits, and 17 we thought was already pretty hard. But that's the next step that you need to take to show that the larger code distance logical qubit performs better than the smaller code distant one. And then something that we're looking into is to perform logical operations between logical qubits. And with that, I'd like to thank you for your attention and thank our team at ETH for putting in all this work into this big effort. As I told you, it's been a 6-year project. And it took about 2 years to get sort of the final stages of this experiment, from the first working 17 qubit chip in our fridge to the final experiments there. And sort of, if you're curious, I can also tell you a bit what the main technical challenges were in achieving these goals. And this was a picture that we took last summer, when I think Switzerland was always quite relaxed with COVID rules, and that was during last summer. We were able to meet with up to 50 people. So this is, I think, is 49, and this has both the students from the previous term and the students from the next term. So as I told you, we have quite a few students in quantum engineering and in physics that are interested in working with us, and so I would think that maybe 40% of the people that you see on this picture are students doing sort of a term or 2-term projects in our lab. All right, thank you very much for your attention.
I guess we're a bit over time.
Yes.
Maybe we have time for some questions. Christopher.
So what's hard about adding more physical qubits?
Okay, so the question is, what is hard about adding more physical qubits? So one of the aspects that was good about this device here, if you look at it, in 17 qubits, it sounds a bit surprising, but every qubit but one is essentially at the edge. Yeah, so you can bring your wiring in from the edge to all but one qubit that sits in the middle. And so this device uses crossovers to route some of the signals there. And for example, if you need something with significantly more qubits, you need to do what Google and IBM and others have demonstrated already. You need to kind of bring wiring in a way that allows you to do better crossovers without harming coherence too much. And I think IBM and Google also see that in their flip chip technologies, their coherences are worse than in their planar technologies. And it's to get flip chip technologies working well, it is a real challenge. And if you look at it currently, who has good flip chip technologies, it's essentially IBM, Google, and Lincoln Labs. And for an academic lab, even a sort of a biggish one, this is a major challenge. So I think we're exploring how to go a bit further with planar architectures, but we're also working on 3D integration, but that's very rough to do in an academic clean room. It's essentially getting access to all the qubits in the center of the device.
Okay, let's take a question.
I guess my question is kind of related. And is the plan to just make a bigger and bigger surface code, or are there potential, other codes that you can look at?
So would we make a bigger and bigger surface code, or do we look at other codes? I think looking at other codes would be interesting. I think we also want to, in principle, you could look at it. I think, for example, if you analyze it from the theoretical level and you want an error threshold and you look at the current hardware, you could ask yourself, okay, how large does the code need to be for this to work? And it looks pretty depressing. You need very large codes with very large overheads, and you don't really want to do that, but you probably would want to get the ingredients work better so that you can maybe live with smaller code distance. And to do clever things about maybe adapting your code to the dominant type of errors in your device, I think that makes sense. So in our instance, so one of the things that you note, the performance in terms of logical phase error and logical bit flip error was very similar. And the main reason is because we do all this spin echoing in our device. So everything gets symmetrized. And so it's homogeneously good both in phase and in bit flips. And obviously, if you use other types of physical systems, for example, ones that use bosonic codes or so, where you can make the errors very asymmetric, then you would adjust your code towards taking care of that. I think you probably have to do a good balance between making the ingredients better, and you would wish for not having to make the code too large, because you get this large overhead to getting only one logical qubit out of every 17 or maybe every 49 or whatever distance you need in the end, physical qubits that you put in. And to not have the overall qubit number too large is certainly something that one would look forward to.
Maybe we'll try and take a question from online. If there are any.
Are there any questions online?
If no one else has one, I have another one. This is Nicole Younger-Halpern again. Could you say something about how you are refreshing the auxiliary qubits between cycles?
Okay, good question. So okay, you heard the question. So we're not refreshing them at all currently. So there's no reset. We just construct our error syndromes by looking at when the auxiliary qubits change state. Yeah, so if there was one error, they go from 0 to 1. And if the coherence is good enough, they will stay in 1. And if there's a second error, they'll go from 1 to 0. And our analysis looks at the change of the auxiliary qubit. And so this maybe makes the leakage error problem a bit more prominent. And one of the next experiments that we want to do is we want to actually physically reset the auxiliary qubits and see whether that affects performance much. But currently it's decoded. We are just taking into account that we are just not resetting auxiliary qubits altogether.
Okay, thank you.
There were a few more questions here.
Yeah, I'm happy to take more if people are willing to stick around. Yeah.
So do you think crosstalk can be a problem here because there are crossover between the
So the question is about is crosstalk a problem in this device, and it is. So there are some instances of where crosstalk is more prominent than other instances, and in particular when components cross over each other. You know, for example, as I said, this one is the central qubit here. So there's a drive line that comes to the central qubit that crosses all sorts of coupling resonators. And depending on what the exact frequencies are that you're trying to drive the qubits with that are coupled to this coupling resonators, you can actually get enough cross capacitance at this crossover here that this could be bothering. And you would like to suppress that on a hardware level by making devices that suppress that, by maybe reducing the crosstalk. And I know that there's labs that are trying to essentially put a shielding layer between the bottom signal wire, the top signal wire, having a sort of a screen between it. That seems to help. And what we did for this device, we actually did do active compensation. So we measure the crosstalk, and then we put an interferometric signal on one of the lines that go to the other qubit to kind of null out that. And that's clearly not something that you can do for an arbitrarily large device, but that worked on this scale.
Yeah.
So it's hard to go to 49 qubits on the same chip, but can you go to 2 logical qubits?
Yes. Yeah. So yeah. So yeah, we're looking at that. So that's something that would actually be on our next list to do.
You talked about having one top of each other.
No, I think this would be lateral. So I think there was this question about transverse gates and comparing like how good your logical error would need to be per cycle. And the easiest transverse gate is indeed when you can do logical gates between every physical qubit, and then you could think about putting them on top of each other. And I think that could even be possible, but it's maybe not the thing that you want to do in the long run, or I'm not sure whether that's something that you want to do in the long run. So you would more likely do lattice surgery in a planar lattice. And I do think that one can do interesting logical gates between logical qubits still in this planar geometry. So I think we're certainly looking into that to see how far we can push that without 3D integration. While I say we do work on 3D integration, but it's significantly harder in all sorts of ways.
So that's sort of what's almost the last part of the question. So it seems to me that you can't continue putting more microwave lines down into your price. At some point, that scaling has to end. So for these things to scale up, how do you anticipate the future for control with an ever increasing number of qubits?
Yeah. So one thing that you see here, like an example of what you can do is there's these dark purple lines that you see, and there's we have multi-frequency multiplexed readout for our qubits, and the multiplexing factor there is 4 or 5. And that's very nice because lots of the expensive electronics is on these readout lines that has all the fancy traveling wave parametric amplifiers and high electron mobility transistor amplifiers. And that brings down cost. And you would certainly like to multiplex in some form on the control side also, maybe with with clever addressing techniques or local filtering, and this is needed. And the question is, like, how large a factor can you gain from this? Can it be 5 or 10 or so? And I think this is an interesting question to see how you can achieve multiplexing in these architectures, and how much that allows you to bring kind of the limit for scaling up. I think, for example, if you now look, so in one of our European projects, this cryogenics manufacturer Blueforce is a project partner, and they have realized this high density wiring systems, and we have cryostats in which we bring down 25 cables in a certain area, and they have versions where they, through the same area, bring down 160 wires or so. So I don't think that the wiring itself will be the limiting thing for now. I think it's going to be pretty expensive and difficult to handle, but and certainly if you think about the long-term scaling, you need to look into it. But I think it's not the dominant problem now. So we can move ahead a bit more for a few steps.
Okay, maybe we'll just check again online, make sure people can participate.
Any questions online?
Yeah,
it's time for lunch.
Here. So thanks everyone.